So I think many of you are still joining. So let us wait for some time and also ask your friends to join soon because we have last few lectures left and I want to begin with something very important. So I'm waiting for 2 minutes for others to join. Done? I think Varalakshmi Madam has completed that part, right? So you know what is multi-layered feed-forward network and how to train multi-layered feed-forward network with back propagation. Those things you know, right? And is anyone studying deep learning? Have you started reading anything about deep learning? I believe some of you have already started studying deep learning. So I try to finish the course content a bit soon in a way that we can have few extra lectures, 2, 3 lectures maybe, on which we can talk about advanced topics, which would be useful for your further developing your career in the area of machine learning. Not that the content that we are discussing is out of syllabus, but it is a bit advanced topic of a bit advanced nature and which are more relevant or related to today's work or the work that is going on in the industry. So we'll end clustering here. We talked about k-means clustering and hierarchical clustering. K-mean is an example of a centroid calculation method or centroid-based clustering. Hierarchical is agglomerative clustering, which is hierarchical of nature. You create cluster hierarchy. Then there are other type of clustering which are called density-based clustering and distribution-based clustering. But that I am leaving to you. Like you explore yourself. They are not very difficult. For example, you can look at DB scan algorithm to look at density-based clustering algorithm. We will come back to this through lab or lecture if time permits. But otherwise, uh, I think you can do it yourself. So that part I will not touch upon. I will start talking about now something more important, that is deep learning, and that I will do through a problem. So a problem, a new traditional machine learning technique, and a new deep learning model. These three things we will discuss in 3 lectures. So that is the idea. So let me share the screen. So the kind of problems that we have discussed so far, there are 3 types, right? One is where One is see the input and decide class label. That was one type of problem that we have discussed. Second was and the third was group similar input examples, right? As you know by now that we have name for this also. This is we call classification. So it's very rough definition, but let's just try to intuitively understand what it is. Classification and clustering. So in one case, we look at the example and identify class label. In second case, we look at a sequence or a input and try to find out a common theme to decide a particular function. Maybe we can also call it function approximation. We look at the data and try to identify the underlying function, which is common theme of everything. And in clustering, we group the similar input examples. We see that how related the input examples are, and we try to group them. So this is from where this centroid-based, density-based, or hierarchical kind of clustering technique emerge. You look at the density and try to relate the example. You look at the distance or similarity and try to group the example. Or you construct the hierarchy and pairwise group the example. So there are kind of different way of grouping similar items, which we call clustering algorithm. But in all cases, if you have noticed, uh, examples are treated independently. Right? Uh, it will be very soon. It will be clear what I mean by this. It means that when you are deciding the outcome for one input example, in case of classification or regression, you do not need to worry about the outcome of previous input example. Similarly, in clustering, while you are comparing the two data points, when you are comparing the two different input examples, you only need to look at the similarity or differences between the two data points only. You don't need to worry about what was computed previously. So what I mean by this is outcome of previous example does not influence the outcome for the present example. This is what I mean by this. For this, all these three, I'm making a very general statement for all three of these. Do you agree with me? Very simple thing, but intuitively this has to be very clear. So is this clear what I'm trying to convey here? Can someone confirm? Is this understood? Any questions on this? Okay, Muna says yes, it is clear. Prince also says clear. Okay, good. So now, then, so why I'm talking about this is because we are characteristics. For example, there are problems for which the output depends, the outcome of the current outcome for the current sample depends on what you have observed earlier and what output was produced earlier. Can you think of any such problem? Any such example? Try to quickly scan through all the programs or all the examples that we have discussed so far in this course and see if you can find out any problem of this nature. Can you think of any such problem? So, so one input is output. So I'm talking about problems in which output for the present input depends on previous inputs and corresponding outputs. Priyank says gift sampling. Gift sampling. So in gift sampling process, yes, we look at the surrounding uh, values, but it is not a problem. Gift sampling is a technique, right? Gift sampling is an algorithm which you can use for classification or for training. But we will use something similar to that. But now I want to draw your attention this kind of problems in which output for the present input depends on previous input and corresponding output. There are many such problems. That's what I say. The range of important, interesting problems are left out. For example, so the live captions that you're looking at in this Google chat is an example of that. Right? It makes many mistakes, as you can see. It depends on the person who is speaking. It depends on the network quality. Depends on the way data is received. But see, if you notice that what was predicted, the previous were predicted, plays a role in predicting next word. So when I'm speaking, if I say I, then you know that I would follow by am and not uh, some other verb, isn't it? So similarly, when I speak Taj, you might expect Mahal after Taj. So the previous word influences the selection or prediction for the next word. So this is kind of one such problem. Second problem, which we want to explore in more detail, is called, for example, the word is Ram eats an apple. The corresponding tags will be proper noun, verb, article, and noun. This is called part of speech. Ram is a proper noun, eat is a verb, an is an article, and apple is a common noun. So the problem is, given a sentence, identify part of speech of words. Part of speech I will refer as POS. So input is a sentence and output is part of speech of every word of the sentence. So Ram eats an apple. The Ram is proper noun. Eats is a verb and is an arc. Apple is a common noun. So this is a kind of a problem where the previous output and input helps you deciding the next output and input. Right? For example, if I'm writing an article, if you see an article, if you know that this part of speech is an article, then the next has to be, you can form a rule that, or you know a rule that article is followed by noun. Right? In English language, article is followed by in. So the previous detection, previous input and corresponding tag helps in detecting the next tag for the next word. So previous word and tag. previous word and tag has to be detecting next word. Right? So we want a model where you want to get the previous input and output and use it to predict the tag or label for the next input, which we are not doing, which we have not done so far in classification of question. We have not done this. So this is a different type of problem that we are talking about, and this kind of problems are known as there is an underlying sequence in the labeling activity that we are doing. We are assuming that the class label for every input item is independent, and we are deciding class label for every input without thinking about what was the previous class label or what was the previous input. Now we are saying that the sequence, the labeling is a sequence, follows a certain sequence, and it is helpful to know the previous input and sequence to predict the next sequence, next label. Right? So this is kind of sequence labeling problem. Is the story so far clear? Is the problem clear? The important point that I want you to note is that the kind of problem that we have started discussing from today is different from the problems that we have solved so far. Right? Is it clear? Can someone confirm? Okay, Prince says, okay, good. So remember this, that was first part of our story, where we introduced the sequence labeling problem and an example as part of speech tagging. Let's come to the next part of the story. So we are going to talk about a specialized graphical model called hidden Markov model. It is a specialized graphical model, and it is an application of expectation maximization and dynamic programming. That is also why I want you to learn this model, because this dynamic programming and expectation maximization both are very interesting algorithms that you know. So it is good to see them working in one application. And the application that we are going to talk is called part of speech tagging or sequence labeling. So recall from our discussion of expectation maximization, we are given data x1, x2, x3, and x, as you can see on the right side of your screen. We are given data points, and some values are not known, which we call hidden variables. That's why we name h. So if the theta parameter is known, parameters I have put on the right side, on the left side is a square box. The parameters are mu and sigma, assuming that we are talking about Gaussian model. If we are talking about Bayesian model, then the parameters would be the independent probabilities, x1, x, ch, and so on. So if the parameters are known, we can calculate this unknown h. So what we do is we start with random initialization of the parameters. Right? In expectation maximization, we start with random initialization of the parameters, and based on the random values that we had assigned, we calculate new value of h. So one unknown is solved. Now once the value of h is known, we go back to maximization. We maximize the parameters, the likelihood that we want to maximize. And based on this x1, x2, and x, we re-estimate our parameters, probability or mu sigma, whichever way you want to go about it. So you re-estimate and update these parameters. Once these parameters are updated, again recalculate h and so on. So keep on this. until you reach a stable assignment. A stable assignment in a way that there is no further modification in parameters, or the parameters change of value in parameter is negligible. Then we stop. Right? This was our EM framework. Just keep this in mind also, so that we can come to the problem. So let us come to the model that we want to discuss. It is again a Bayesian network. You will automatically identify it as you see. It is called hidden Markov model, or HNM. And we are going to study HNM with respect to part of speech tagging. So let us again come to the example that we are talking about. Ram eats an apple. There is input sentence, and what we expect as output is Ram is a proper noun, eat is a verb, an is an article, and apple is a common noun. This is what we want. Now, if you want to look at this as a Bayesian network, then you can model all of this as random variables. Ram eats an apple, MP, VB, AT, and N. Everything is a random variable. And in this random variable, the part of speech are class label or unknown hidden variables. And words are the observed variables. Again, go back to the expectation maximization framework. Then x1, x2, and x3 are observed random variables, and h is hidden or unknown random variable. Continuing the same formation, here we can say that the part of speech labels, that is noun, verb, etc., is unknown hidden variable, and words that we see in a sentence are observed variables. What is the difference here? What is the one important point to note here is the random variables which are part of speech label is finite for a language. A language has finite type of part of speech, like article, noun, verb, adjective, adverb, pronouns, and so on. But it is finite, right? There can be 10, 20, 30, but it is anyway finite. So the class label that you want to choose is a finite. And the random variables that you observe, which we call words, is a data point, and it is infinite. A language can have, though it is a very huge finite set, but we can say infinite, because as you keep on adding a word in language, so infinite. So the set of words is, can arguably say it is an infinite set. So what we do is, we do part of speech as a class label, words as data point. And a word can have more than one part of speech also, right? So there is a reasonable amount of ambiguity involved in detecting part of speech also, like will is an auxiliary verb, can is also be a noun, and so on. So there is second important part of this problem. And the third part is, given a sentence, can we disambiguate part of speech of a word? For example, the play was good. So the is determiner here, and play is noun. And the rule that we know is noun follows determiner, or determiner is usually followed by a noun. And the second sentence is, boys play cricket. In this case, the first word was noun, and second word is play, which is a verb. And the rule of language that we know is that noun is usually followed by a verb. So the word play can appear in two different parts of speech, one as a noun, second as a verb. And to decide the part of speech of word play, we need to look at the previous word and its corresponding part of speech. Right? This is a very crucial point in this modeling. So I want to make sure that you all understand this. Right? So first sentence I'm saying is word play can have more than one part of speech. Right? And as you can see in example, there are two. One is noun, second is verb. Now, which is the correct part of speech for the word play? That is decided by the word and part of speech that you have observed before the word play. In first example, you have observed a determiner the, and that's why you call play a noun. In second example, you have observed a noun boys, and that's why you assign label verb to the word play. Right? So does this fit in our description of sequence labeling with which we have started our discussion? Right? Do you see the importance of sequence here? Why you need to know the previous answer to predict the next answer? Right? So that's why this sequence labeling is important. And that is our point. The tag of previous word helps in identifying post tag for the current word. So now the model that we are preparing is something like this. This circle and square or rectangle, both are random variables. Just I have tried to distinguish between the hidden and observed. Rectangle is observed word. So there is also observed state. These random variables are actually states now. So you can have word 1 and state 1. Why am I calling this state? Because now if you go back to this example, the play was good. Then when I am disambiguating play, I am in a state where the previous word was the and previous part of speech was dt or determiner. So I am in a state where the previous part of speech was determiner. In second sentence, I am in a state where previous part of speech was noun. If you have seen a determiner first, then you cannot predict the next word as also as determiner. There cannot be two consecutive determiner in a language. So a determiner is observed means that you have moved to a new state where you don't see any determiner. But mostly what you will see is a noun. Right? So S1, S2, S3, Sn are the states which are hidden and which is an assigned part of speech for a word. And state S2 depends on S1, as we have sufficiently emphasized that noun, S2 can be noun if S1 is a determiner. S2 would be verb if S1 is a noun. Okay? So previous assignment makes or helps in deciding the next assignment. So that's why there is a dependency. So assignment of S2 depends on S1. Assignment of S3 depends on S2 and so on. So that is how the conditional dependency is modeled. And if you notice, here we are only looking at the previous assignment, not the one before that. So to decide part of speech of S3, you only want to look at the part of speech of S3. You don't need to look at part of speech of S1 directly. Indirectly maybe, because you know that this is noun, then this might be determiner or article or anything. But once it is noun, it is sufficient for you to disambiguate S3 or to decide part of speech at S3. So this makes a change which we know as Markov change. Right? We also know Markov assumption that the current state or current random variable depends only on neighbor or immediate neighbor and not on anything else. So this Markov assumption helps here also. And so you know that from where the name came. The name is hidden Markov model. Hidden is part of speech variables, state variables, which we have modeled hidden variables. And we make Markov assumptions for this hidden variable. So that's why it is a hidden Markov model. And what we observe is W1. So depending upon the part of speech, we observe word W2. So we have two kind of probabilities to deal with here. One is, or I think you should answer, which are the probability, if you want to decide the parameter of this model, which are the probabilities? Can someone tell me the probability of this model? It is very simple, right? From your Bayesian network knowledge. What are the model parameters of this? Model parameters are, look at the arrow, follow the arrow, and you know the probability. Probability of W1 given S1 and probability of S2 given S1, right? This is called transition probability, and this is called, this is called emission probability, and this is called transition probability. So what I'm saying is the part of speech emits a word. If I say part of speech is an article, then you can emit three corresponding words in English: A, N, and B. Okay? So that is emission probability. What is probability that you have seen an article and you are emitting A? And what is probability that you have seen an article and you are emitting AN? And transition probability is, what is probability of transitioning from an article to a noun? What is probability of transitioning from a noun to a verb? What is probability of transitioning from an adjective to a noun? So that is transition probability. This is a simple formula. We'll see more detailed formula very soon. But is the model clear? Are you with me so far? Can someone confirm? Is it clear? Is it clear? Any questions on this model? Or is it clear? I'm waiting for some confirmation and then I will move to the details. Can someone confirm? Birwa, Vishrut, Kenil, Vidit, Shubham? Are you listening? I'm not sure if you are paying attention. Vishnu says yes. Love says yes. Okay. Birwa, as usual, is not paying attention. Okay. So this is the model, right? And what we are assuming is it only depends on immediate previous state. Sn depends on Sn minus 1 only. This is where we are exploiting this Markov property. And our probabilities are, probability of Si plus 1 given Si is called transition probability, as I say. And probability of Wi given Si is called emission probability. So the complete model would look like this. So we want to predict state Si, that is part of speech for ith word, given all the previous words observed and all the previous states. Priyank is asking here, hidden state is QS or word of sentence. Hidden state is part of speech. S, S state stands for part of speech label. Right? So if you see here, the circle S, S1, S2, S3, these are part of speech labels, and the rectangle W1 to Wn are observed words. So hidden states are part of speech, and observed states are words. Right? So probability of Si, that is we want to predict part of speech for the word I. What we have seen so far is we have seen word I to I minus word 1 to word I minus 1, and we also make prediction for their state S1, S2 to Si minus 1. So how do we calculate this now, given these two transition and emission probability? So it will be as shown in this formula. Pi of probability of Wi given Si, that is the current word that you are looking at, into the previous state that you have predicted, Si given S2. And this is for all I, that all words, for every word you need to do it. And so if a sentence has 10 words, then 10 such multiplications. And you are starting with an initial state called S0. So we need to define an initial state S0 where no word is observed and no part of speech label is assigned. So something kind of null state. So overall probability of assigning sequence of states to a sequence of words is decided by this formula. And what we want to do is we want to maximize this probability. So expectation maximization would come in picture here. So WS are observed variable, S are words are observed variable, S are hidden variable. And from our Bayesian network, we know that X1 given C, X2 given C, this all we have done many times. Only thing is, S are states which are a bit different from traditional random variable in a way that N, VB, adjective, and W is a cat, dog. So instead of creating a random variable for every word in the dictionary, what we do is we create state W, which can take value from this set, that is dictionary. Similarly, we create a state S, which can take value from this set of part of speech. So this is how it is different from traditional random variable. So n number of states is equal to number of words in the sentence. So if a sentence has n words, then you want to create n words. And what is not known is S1, so that's why it is called hidden Markov model. And initial state is pi S0 or PSO, which is initial state. And as I said, transition probability is PSI given Si minus 1. Emission probability is PWI given Si. Right? Is the setup clear? Any question on the setup? Right, so prepared the model and decided all the parameters of the model. What is left now is training. How to calculate this transition and emission probability. If we calculate these probabilities, then we can answer for part of, or we can identify part of speech of a sentence. Actually, I'm waiting for a minute for you to rewind all the things that you have discussed so far. And please ask me if you have any questions here. Okay, so if there are no other questions, let's move on. So how do we train the system? The H&M is a kind of mix of supervised and unsupervised learning. So we'll talk about first we'll talk about supervised part where we are given a text corpus with every tag. So for example, the boys play cricket. So word and corresponding tags are known to us. The is determiner, boys is plays verb, cricket is noun phrase, sorry, proper noun, ram is proper noun, likes is verb, is determiner, play is common noun. If such tag corpus is given to us, then we can create tables to calculate this transition and emission probability. This list of states number them. So let's say SI is list of states which covers all the part of speech like BP, N, VB, NP, BP, and VB, NP. Look at the corpus and calculate this number. So how many times you have seen BP in the corpus? How many times you have seen noun phrase in the corpus? Or how many times you have seen that noun followed by DT? So for example, noun followed DT here, one. So you have seen noun DT combination one and noun DT combination one. So you have seen twice that usually noun follows determiner. So that's why you put number 2 here. How many times you have seen determiner following determiner? Never. How many times you have seen verb following determiner? Never. How many times you have seen noun, proper noun following determiner? Never. So that is 0. So this is a very small toy example with only 2 sentences, but in reality you need thousands of sentences to create this table. But this gives you an idea, right? How to create this table. So this table, this models transition probability from the corpus, and it counts how many times a particular state followed the previously assigned state value. Similarly, create an emission probability table where you see that how many times determiner was or how many times determiner was boys, how many times determiner was play, how many times determiner emits cricket, how many times determiner emits ram, and how many times determiner emits light. So if you see there are two cases where you assign BP in the corpus. And one case it was boys, in second it was play. And both the time determiner was the CHE. So you determine to CHE the. And so on, right? So this is how we prepare our transition and emission probability tables. What next? After once the tables are prepared, what do we do? We have parameters, and now given a sentence, we will use this parameter to calculate probability of all the outcomes, and we will choose the outcome with highest probability. So one such corpus, if you want to explore, brown corpus is one corpus where the words are part of speech tag, and you can use it for your experiment. I have missed this null as a state, right? I have started only with part of speech tag, but null is also state, as I said. So see that how many times null follows determiner, how many times null follows proper noun and verb, and you get the table. So this is training part. In training of hidden Markov model, you calculate this thing. And if you have tagged corpus, you can very easily count this equality. Once this is done, the next thing is inference. Given a new sentence, Ram plays cricket, you want to predict part of speech label for all of these words. How do we do this? So that is done by a very interesting dynamic programming algorithm called Viterbi algorithm. This is called decoding. So most of the time sequence labeling structures have a decoding phase. So decoding phase is where you are assigning class label for or observed input sequence. So input sequence is Ram plays cricket, and you want to decide part of speech for Ram, play, and cricket. And we have total how many labels in our corpus? BP, N, VB, and P. Four labels, and one null label. So we say that first label is always null. By default, it is null. And for first word Ram, we have four choices of label: determiner, noun, verb, and noun phrase, and proper noun. So these are four states. And you look at probability of each of these. Look at the emission probability table and see that probability. What is probability of Ram given determiner? What is probability of Ram given noun? What is probability of Ram given verb? And what is probability of Ram given NP? I have noted down this probability inside the circle: 0 by 2, 0 by 2, 0 by 2, and 1 by 2. If you want to look at the table. Right. So 0 by 2, 1 by, this is Ram and corresponding part of speech label. How many times you have seen proper noun? Twice. Out of those two occurrences, once it was assigned to Ram, so it is 1 by 2. Verb, there were two verbs in the corpus. None of them were assigned to Ram, so it is 0 by 2. And similar for noun and determiner. So this is the emission probability assigned to the first word Ram. And based on this emission probability, the winning label is 1 by 2, that is proper noun. Ram is a proper noun. It is correct also for our example, but it does not end here. We want to maximize the probability of entire sequence. So one assignment will not be sufficient. We want to find out the base set of labels or base sequence of labels for this sequence of words for which the overall probability is maximized. And what do I mean by overall probability? By overall probability, I mean this. This multiplication has to be maximized. This pi PWSI into PSI by SSI into PS0 has to be maximized. So we do not, with this first assignment, we know that the proper noun is winner here, but we do not discard other sequence. What we do is we create a graph, we continue with the next word and possible label, and again we calculate the probability of play getting a certain label. But now we have a previous word observed also, so that will be multiplied. So play will be probability of particular part of speech given play multiplied by the previous part of speech that you have observed. That multiplication will go here. And again you will choose a winner. So maximizer here is this 1 by 2. Similarly, you follow the path and reach up to n nodes where you have maximum probability. So that will be the final assignment of the part of speech to word. Right? So this is kind of dynamic programming. As you can see, in dynamic programming, we first solve a smaller problem and then we go to the larger one. So here, smallest problem is disambiguate only one word. So this is dynamic programming level 1, initialization, assigning part of speech for the first word. Then use the solution. What is the idea of dynamic programming? Use the previous solution to construct the larger solution. So at level 2, we have used the previous solution and our formulation was multiplication of the current probability, emission probability with the previous transition probability. So we reach level 2 and so on. Ultimately, when we reach the final level, the maximum value that we find, the path for which we find the maximum value is the optimal probability assignment for the sequence of words. Right? So this is Viterbi algorithm. Right? So that is our story of hidden Markov model. And I think these examples are not given to you, so I will not go to that. Boundaries also means keys for a while. Yeah, so that's it from me for today. Ask me if you have any questions or any doubts on this. So if there are no other questions or doubts, we'll end here. And next time, we'll do something to make sure that you got this idea, maybe through program or through some lab assignment. And we'll move to the recurrent neural network where we can try to solve the same problem, part of speech tagging. And then we can have a comparative of HMM versus recurrent neural network. And so I will end with this. Thanks.